In this video, I'm going to take you through non-exact differential equations. In our previous lesson, I taught you how to solve exact differential equations. Now, one may ask, if I test for exact differential equation and I found out that it is not, how do I go about it? So there are situations where you know that generally exact differential equations are represented by m of a function xy dx plus n of a function xy dy is equal to 0. To prove that this is an exact equation, it is expected to differentiate the function attached to the dx with respect to y, so d of m of xy over dy, and this should be equal to d of n of xy over dx. Once this condition is satisfied, we can say that the differential equation given is an exact differential equation. If not, it is not an exact differential equation. Now let's see what to do if the differential equation is not exact. If the differential equation is not exact, we need to transform it from the non-exact to exact. So how do we transform it from non-exact to exact? We use integrating factor. So we need to find the integrating factor in order to transform a non-exact differential equation to an exact differential equation. So let's see, how do we find the integrating factor? We can find the integrating factor by two conditions. The first condition is when you take 1 over the expression or the function attached to the dx, that is 1 over the function m of xy, multiplying the expression d of mxy over dy minus d of nxy over dx. This expression here should be equal to a function of what? Y. So when you divide this expression here by m of xy, then you should get a function of h of y. Now, once this condition is satisfied, we can say that the integrating factor IE is equal to e to the power negative integral of h of y dy. The second part is saying that when you take 1 over n of xy, that is the function attached to the xy, when you divide it, multiplying this expression, d of mxy over dy minus d of nxy over dx. Once this expression here is simplified, it is expected to get a function in only x, that is g of x. So once you get a function in g of x, then our integrating factor becomes e to the power integral of g of x dx. So once you have our integrating factor, to convert it from non-exact to exact, what we need to do is to multiply through our equation by the integrating factor. Then our equation will then be an exact equation. I've talked a lot. Let's take an example for us to understand how to convert a non-exact to an exact differential equation. So in my example, I have y dx minus x dy is equal to 0. This is a differential equation given to us for us to examine whether it is exact or non-exact, then see the necessary thing to do. First, let's identify if this equation is an exact equation. For you to identify it is an exact equation, the first thing to do is the function attached to the dx will be differentiated with respect to y. So I'm going to have dy here, I'm going to differentiate this expression y with respect to what? Y. Then I will differentiate the expression attached to the dy with respect to what? X. So I will differentiate the x here with respect to what? X. And in these two situations, you realize that the standard form for our exact is mxy dx plus nxy dy equals 0, meaning the sign here is plus. In our situation, the sign here is minus. For that reason, you add a negative side to this side. So you realize that this will give me 1, this will give me negative 1. They are not equal, hence our equation is not exact. So this is a true scenario of non-exact differential equation. How do we convert this to an exact? We need to do this by finding the integrating factor, i.e. How do we find the integrating factor for non-exact? To do that, I gave a formula that 1 over the mxy. So the function attached to the dx here is now y. So when you have that, 1 over mxy become 1 over y, multiplying the derivative of this function attached to the what? Dx, we are going to differentiate that with respect to y, and that will give me 1, then minus this one with respect to x, and here we had negative 1, so negative 1. So we are actually subtracting the result of doing this minus the result of what? Doing this, and this should give us a function of what? Y. So let's see, this here is going to give me what? 1 minus minus 1 will give me 2 over y, and indeed it's a function of y. So our integrating factor I becomes integral, e to the power integral, negative integral of what? The g of y dy. So once we have negative gy dy, we just make our substitution, and you realize you are going to get negative integral of g of y. So our g of y now is 2 over y. So let me bring it 2 over y. So you have 2 over y dy. So let's see, e to the power. So with this expression here, I'm going to integrate this. So negative 2 is now a constant, so e negative 2 will come out, integral 1 over y dy. Integral 1 over y is ln y, so I'm going to get e to the power negative 2 ln y here. There is no need adding the constant, so we're going to have e to the power ln y to the power negative 2, and you know e to the power ln, you get this. So our answer is going to be y to the power negative 2, which is equal to 1 over y squared. So now our integrating factor I is simply equal to 1 over y squared, and this is how we find the integrating factor. Once you have done this, then the next thing to do is to multiply this integrating factor through the equation. So I have y dx minus x dy equals 0. If I multiply through this equation by this, I'll get y squared here, y squared here, y squared here, and I'm going to get here, I'll get dx over y minus x over y squared dy is equal to 0. Now let's test if our equation is now exact equation. Let's see if our transformation is true. To see that this equation is now exact, what you are going to do is you still use the condition differentiating the function attached to the x by the y. So if we differentiate here with respect to y, we are going to get the derivative. So here is the same as y to the power negative 1. So negative 1 will multiply this, and you subtract 1. So this is going to give me negative y negative 2 here, which is the same as negative 1 over y squared. When I differentiate a term attached to the dy with respect to x, I'm supposed to get what? So if I differentiate with respect to x, the function attached to this is what? This whole thing, negative x over y squared. If I differentiate this with respect to x, this is a constant, so this will give me 1, and the answer will be negative 1 over y squared. Hence, they are now equal, and I have been able to transform my equation to an exact differential equation. So right now, my transformation is correct, and my new equation is dx over y minus x dy over y squared is equal to 0. So this is how we transform a non-exact to an exact differential equation. At this point, we are just to solve this simply by separable. So dx over dy will be equal to x dy on y squared. You can choose to use the normal exact. So let's first use separable to do this. So you see, so when I have this, I can separate my y and x so that I'll have my x here and my y here. So dx over x will be equal to y dy over y squared. I'll interchange the position. So once I have this, I'm going to have dx over x will be equal to dy over y. Then I integrate both sides here with respect to what? Dx, here with respect to dy. So when you have this integral of the x on x with respect to x, I'm going to get ln x plus c. I'll get ln y plus what? Let's say k. Then ln x, I'll send a c. When you have two constants on both sides, you can combine to get one constant on one side. Ln y plus k. So once I get something like this, my goal here is to make y the subject, right? So when I send it there, it doesn't change to negative k because it's still a constant. So let me make it ln x plus k is equal to ln y. Then I can say that e to the power ln x plus k will be equal to y. Then this is the same as e to the power ln x multiplying e to the power k is equal to y. You know that e to the power k is still k, but e to the power ln x is x. X will be equal to what? Multiplying what? K is equal to y. So therefore y is going to be kx, where k is our constant of integration, and our differential equation has been what? Solved. And that is how we go by our exact differential equation. Using exact to solve this, you see, this was our transformation. We used separable. Now note that every separable differential equation can be solved using exact, and every exact can be solved using separable. We try using separable and we've got an answer to be y equals ks. Let's see using exact. Exact is saying that you will integrate the side which is attached to the dx with dx. So integral of 1 over y dx, then you integrate this with respect to y. Integral of x over y squared negative x over y squared with respect to dy. Then after we merge, then after we are going to merge it. So here is going to give me what? Ln of what? Y. And this will give me integral with respect to y. Here I had over y squared here. So let's see. Here was with respect to x, sorry. So with respect to x, I'm going to get x over y because y here will be a constant. Then with respect to y here, with respect to y, I'm going to get what? If you have the x here too will be what? A constant. So negative x integral of what? 1 over y squared dy. When you have this, the same as y to the power negative 2. You add 1 and it becomes negative 1 over negative 1. So I'm going to get x over y for this side. Then for this side, I'm going to get the negative, and the negative here will be positive. So I'm going to get x over what? Y. And you realize that they are the same. Once you get the same thing, you choose 1. So x over y will be equal to the c. Hence, y is equal to what? So here you can say x is equal to yc, and this is just a constant, right? So you realize that, so we are going to realize that our differential equation once solved with this was equal to what? This. Thank you for being with me in this video. Please subscribe and follow me in my subsequent videos.